a voltage regulator. And this X also depends to the amounts of the voltage which will be provided by that voltage regulator. So stop writing and look on the blackboard. Let me give you examples and explain the meanings of this series. So some examples, you say that in electronics, we have a voltage regulator, positive voltage regulator, which is called LOM7805. You see, remember that the series is LOM78XX. Wait! So X here is 0. The second X is what? A? 5. The second example, we have also LOM7806. What does it mean? This 05, it means that it provides the positive 5 voltage, which is regulated. What does these two numbers mean? This one will provide the output voltage or output regulated voltage of 60 volt. Okay? But it's fixed. It does not vary. Then the third example, we also LOM7807. I said stop writing, stop drawing, and stop slumbering. Look on the blackboard. So then we have a fourth example, LOM7808. Then we also have the fifth example, LOM7809. So this provides 80 volt, 7 volt, 9 volt. Okay? Then we say number 60, we have LOM7812. We don't have LOM7811, so don't cram. That will be adding by 1, adding by 1, adding by 1. Because in Bongoland, we cram. So you just learn these 5 and then you say, so now I understood. I got revelation. So for the voltage, you just say add 1, add 1, add 1, add 1. No. Because we don't have anything, we don't have a voltage regulator which does not have a particular function. All of these standards have been set according to what amounts of the voltage we use in operatings or different electronics devices and the equipments uses for the particular functioning. Because for example, a television receiver, it consumes different voltage in different sections. Even your mobile phones is consume different voltage in different sections. So all of those voltage regulators have been manufactured for the particular purpose. They are not manufactured for just for leisure, or just to tell you that you have a voltage regulator of LOM7811. Wewe, Matatu, and your neighbor. Your neighbor on your left hand side. Then the seventh example, LOM7815. Give me a pen. And then so from there you listen. Precious, keep yours. Number 8, LOM7818. When I ask you to be attention and focus and listen, look. These are the information which do not need you to repeat several times. For instance, myself, I learned 9 years ago, and then it's stuck in my mind. It's not the information that you have to go and restart and restart. When you listen careful, you just keep those numbers. They are not tough. So when you think about linear power supply, you have to know what are the available voltage regulators. Okay? Then the last one, that's example 9. The last one, we have LOM7824. Forget these standards or forget. Don't relate what the voltage regulator provide with what the step-down transformer provide. We have spoken about the specification of the transformer. We are done with step-down transformer. Now we are talking about voltage. Voltage regulators. Are we together? Are we together? Eh? Yeah. But in our country, this is the mostly found. This one, this one, this one, You may find this, but they are rarely used. Possibly this one. Okay? Okay. So that is LOM 7830 X6. Okay? So right now, because I know that you have a hunger. You are hungry in writing. Especially if you understand. You say, let me write. Okay, right now. Because usually in Tanzania, we don't tell the students write. They just write themselves. Why? They believe in writing rather than in understanding. Then we say that the standard series of negative voltage regulator, regulators I see, is LOM 79XX. So now it's a time where I want to tell you that stop writing. I didn't say stop writing. I'm about to tell you that stop. But others, they have already finished it to copy. So we mentioned about negative voltage regulator. Ask your neighbor, where do you use them in electronics? Huh? Where do you use them in electronics? If I just remember about the amplifier, the transistor amplifier, we always use either positive 12 DC or positive 15 or positive 18 volt DC. Where are we using these negative voltage regulators? Where do you use in electronics? I said, ask your neighbor. I said, ask your neighbor. Ask your neighbor. What did they ask your neighbor? What did they told you to ask your neighbor? Because I asked you to ask your neighbor to give you an idea where do we use negative voltage in what? In electronics. So, but Johanna was concentrating on what? On copying the notes. So I asked him to ask his neighbor. Then he said, ask what? Okay, so examples. Hey, stop writing now. Check your neighbor, take your neighbor's pen. Take your neighbor's pen. And it should be black and yours should be blue. So the examples are just like this way. So we have LOM 7905. So this one, when we discuss about the output voltage, let me just add something. Output voltage. So for the output voltage for this case is 5 volt, positive 5 volt. This one positive 60 volt. And this one positive 7 volt. And this one is positive 80 volt. And this one is positive 9 volt. And this one is positive 12 volt. And this one is positive 15 volt. And this one positive 18 volt. And this one is positive 24 volt. So for this case, here we have what? LOM79XX. And here we want to discuss about output voltage. So for this case, we have LOM 79. Check your neighbor if he or she is listening. Check your neighbor. LOM 70 what? 0 what? 5. So this provide negative 5 volt. The next example, LOM 79 0 what? 06, negative what? 60 volt. Then LOM 79 0 what? 7. 7 what? 7 volt. Then LOM 79 0 negative what? Then A. You cannot mention because you are right. Look. Mexina, look. Yes, Mexina and Shukuru. They are right. Dixon, LM what? The boss. Hawezi kutaja. Akuwepo darasani. Nimrudisha. LM 70 9 1 Omolo. Next is what? Omolo was not there. Mfunye? Suleiman? This is provide what? Negative 12. Negative 12 mangoes. 09. Okay. So now Johanna is in the class. Negative 9. Then Jessica, LM what is 79 what? 12. Today you are sick, eh? You cannot talk much, eh? Okay. Thank you. This is negative 12 what? Volt. Zuena? LOM 79 15. This providing what? Then Joan? What? 79. You just made 79. 18. Provide what? Volt. Now Mvua, look for Lucia. She has gone out and she's busy outside there. Then Jessica? Next. LM 79? 24. Okay. LOM 79 24. Provide what? 24 volt. So now comes to what you have been asking your neighbor. Where do we use this negative voltage in electronics? According to your experience and according to what you have been learning. Where? What your neighbor told you? For instance, Neema, what did Winfrida tell you? Designing power supply. And what did Neema tell you? She told you nothing. Sure. Okay, ask her now. Maybe you didn't ask her. Ask her in this way. Abdullah, what is your neighbor told you? Do you know her name? You don't know. Ask her name. You know her. What is her name? What's her name? Somebody? Anastasia. Anastasia, do you know the name of your neighbor? What did he tell you? You don't remember? He said that he doesn't know. Digna? Lativa? You don't know. She doesn't know. So she doesn't know and you doesn't know. So he's saying bongo goma draw. Okay, so in most cases we use negative voltage when we are designing or whenever we are using op amplifiers. So most of operation amplifier need a positive power supply and negative power supply for them to function. Because I don't want just to teach you something and they say, we have just learned about negative power, negative voltage regulators, but I don't think if you have any use. No, in electronics, whenever we discuss with analogy, negative voltage supply is very important, and especially for the operation amplifier. If you refer to advanced physics that you've been learning, what are the functions of the op-amp? How many functions did you learn? So can you mention the function of op-amp, Shukuru? Yeah?
Use an amplifier circuit.
Pardon?
Amplifier circuit.
Use the as amplifier circuit. Mexina? Voltage? Use it for voltage gain. My friend here? Hey. Yes. Yes. Happiness, our friend was not in the class. Summing, amplifier. My friend there? Eh? Audio mixer. So audio mixer is all about summing amplifier. Jacqueline? Current gain. Pili? What are the functions of op-amp according to what you have learned in advanced electronics? Pili? Pardon? We have just mentioned summing amplifier. Used in radio frequency. How is it used in radio frequency? Ruben? Used to amplify signal. No, that's it. It's been already mentioned. Adam? UC as differential amplifier. Very good. Salama? Used as oscillator. Joshua? Used in mixer. Mixer is summing amplifier. It has been mentioned. Differential amplifier, it has been mentioned. My dear student. You have forgotten that we use op-amp as amplifier. Just as amplifier. We use as summing amplifier. We use as voltage follower. Voltage follower. We use op-amp as differentiator. Differentiator. We use op-amp as integrator. We use op-amp as the filter. We use op-amp as monostable. 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 We use op-amp as bistable. So we have so many applications of operation amplifier. And they have taught you in advanced electronic science. But now you forgot. Monostable, multivibrator. Bistable, multivibrator. You learned them. Maybe you have been cramming them. So the op-amp, the symbol for operation amplifier, for instance, so any operation amplifier IC cannot be used without a negative voltage supply. Why? Because the symbol, first of all, here the symbol of the op-amp. Because I want to show you where we apply. So this is non-inverting terminal, input terminal. This is inverting input terminal. And then this one is out. And then we say that here we have some other terminal. So this is negative voltage supply, and this is positive voltage supply. So the three remaining terminals are not in use. Because the IC, the standard integrated circuits of op-amp, of for instance UN 741, this is the simple operation amplifier, and this is the notch, it has 4 pins. So if there's 4 pins within it, you can find that most of the op-amp IC or operation amplifier IC have more than one operational amplifier. So we have 2 pins for input, 1 pin for output. This is for the negative voltage supply, and this for the positive voltage supply. So this you can find number 1, number 2, you find this one number 3, for instance number 4, number 5. But also you have some other terminals which are 3. So you can find that one IC consists of 2 op-amp. So here you can have one op-amp 1 on this side, op-amp 1, and here you can have op-amp 2. So simply, this is the point where you need negative. When you say operation amplifier, we're not talking about transistor amplifier. It's something else. Okay? Because when you hear amplifier, you just remember about bipolar junction, NPN, transistor, OBC 400, 570, 47. So that is about 30. So we say that the voltage regulator ICs receive different or receive a particular range of regulated or unregulated voltage depending on its output. So we have different types of voltage positive or voltage regulators ICs. But the input of this, the range for the input of this voltage regulator is different from the range of this voltage regulator. Are we together, class? Okay. Class, stop writing. Listen. I have just introduced you the idea. I didn't tell you about the schema, just the configurations of the voltage regulator. We want to discuss about the input, right? We have talked about the input and what the voltage regulator does actual, and then we have talked about the output. So the input of voltage regulator, so that's what the voltage regulator I see receive a particular range of 40 of input. Input either regulated or unregulated voltage, depending on its output. So for instance, there is a minimum input voltage for this IC, which will be different from the minimum input voltage of this IC. There is a maximum output voltage for this IC before it burnt out, which is always different from the maximum output of this voltage regulator. Do you understand what am I teaching you? In Tanzania or in our own countries, most of these are the negative voltage regulator. You might find this in most of the shops. These four. But especially this one and this one. 5 volts and 12 volts, because in most of the projects we are using 5 volts or 12 volts. Just a few projects where we are using maybe 9 volts. So, example. Let me just teach you this concept example. Example. The range of input voltage of LOM 7805 is 7 volt and 25 volt. So we say that in order for the LOM 7805 IC to regulate any input voltage, the condition is the input voltage should be either 7 volt or greater than 7 volt but less than 25 volt. So if you provide less than 7 volts, that voltage regulator will have nothing to do with the supply voltage. If you provide it with 26 volts, you are going to burn your voltage regulator. Are we together? Yes. Are we together, class? Okay, should I repeat? Huh? I say, this is according to the data sheet. We say that, according to the data sheet, so we say that manufacturer's mind, this is called in electronics, it's called the data sheet. So the manufacturer is the one who knows the specifications of the IC more than anybody else. So the LOM 7805 performs its function when the input voltage is either 7 volt or greater than 7 volt, but not greater than 26 volt. Not greater than 25 volt. So if it receives the input voltage between 7 volt and 25 volts, the voltage regulator will perform its function of regulating or stepping down the voltage and give you the 5 volt. Are we together, class? Are we together? So it's better for you to understand, because for instance, myself, I have made this challenge, and this is the common challenge. You might find that you are just troubleshooting your circuit. It does not give you the 5 volts that you desire, but the reasons might be the input voltage is less than 7. If you provide 60 volt into this voltage regulator, you will never get 5 volt. You will get less than 5 volt. You might get even that 3 volt or 4 volt. And from there you find that it means that the voltage regulator is not performing its function or desired function. Are we together? Are we together? Who say no? Okay. If you did not understand, let me use this concept. This is the physical appearance of voltage regulator. It's rectangular in shape. I gave you. You have a photo of it. And then you can find that here it is written LOM 78, let's say 05. Listen. When you look this voltage regulators in this side, this is in, this is ground, this is out. Hey, hello. So, what are we discussing? This is what we are discussing. In order for this voltage regulator to regulate what you have fed it, it needs the input. Right? Eh? So if it is LOM 7805, then the input voltage V in should be within 7 volt up 25 volt. If you provide less than 7 volt, don't expect to get 5 volt in the output. Are we together? In simulation, sometimes we may get, we may still, those are the weaknesses or challenges that in simulation that they don't figure out. But practically, you might find that you have designed your linear power supply. Today it's providing 5 volt, then you turn off your circuit, you leave, the next day when you come back, and then you turn on, you measure the output power, or the output voltage is not 5. Maybe you can find it's 3.5. Don't expect the other parts to work that need 5 volt. Okay? If you provide more than 25, if you provide input voltage of more than 25 volts to the LOM 7805, you are going to burn. Or you are going to destroy, or it's going to destroy what? Your voltage regulator. Class, are we together? So this is equal to the minimum, and this is the maximum, but you have a typical value. So from there, let me just see, I have found some table, or just a table that can help you to remember about what I've been teaching you. Figure 4, physical appearance of LOM 7805 voltage regulator. Table of input voltage for LOM 78XX series. Who is talking? Eh? Ask your neighbor, do you understand about voltage regulator? Or okay, so I've given you example. You have to go and find for the remaining voltage regulators because I've mentioned almost 18 voltage regulator to actually extend your learning capacity to know what's going on. Possibly you have met only one voltage regulator, which is LM 7805, and then you saw this is enough, I know. So I've just found for you these are minimum input voltage. Stop writing, stop drawing. Listen, I have found just the range, the input range or the input range of voltage for the 6 positive voltage regulator. So it's your responsibility to go and find for the remaining. Because these specifications are very important, and especially if you want to build or you want to build the linear power supply in hardware architecture. So, for instance, the minimum input voltage for LM 7805 is 7 volt, and maximum is 25 volt. So remember that this is very important to know what, because for instance, the voltage regulator unit force block. When you know this range, it's very important to think about the choice of the step-down transformer. Okay? Okay? So for instance, we have voltage 16, 15.2, so it's fine, it's within the range. Right? And then so we have LM 7808, 10.5 volt. This is the minimum. So when you feed, let's say, 9 volts in LM 7808, it won't give you 8 volt. And actually, your entire circuit will be misbehaving. Your entire linear power supply will be misbehaving at all. Okay? So the problem is not the voltage regulator. The problem is your input voltage. Right? And I know that this is the common problems, especially for the prototyping issue. Fulgence here. Then, the minimum input voltage for the AM7810 is 12.5 volt. And the maximum is 28 volt. The minimum input voltage for the AM7812 is 14.5 volt. The maximum is 30 volt. The minimum input voltage for what LM7815 is 17.5 volt, and the maximum is 30 volt. The minimum input voltage for LM7824 is 27 volt, and the maximum is 38 volt. For instance, Mexina, you are scenery. Abduli, greet Dennis. Abduli, greet your friend Dennis. Okay, for instance, our output voltage of what? Of filter unit is 15.57 volt. Right? Right? According to the choice of our step-down transformer, which providing the root mean square voltage or output voltage of 12 volt. Okay? Yeah. So for instance, if you take this input voltage and then you want it to regulate it, and you have you are supplying that 15.57 volt to LOM7815, then you will never have 15 volt as output. Why? Because the input voltage is less than the recommended input voltage of LOM7812. That's the point when the problem starts. Matatu, 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 matatu. Is it clear or should I repeat? Eh? I have to repeat. Why? Because you are not in the class. I say stop writing, stop drawing the table. You will just draw the table. Don't worry about the table. You have so many tables, but you have never understood them. Let me repeat. The output voltage of the filter unit that we have in our design is 15.57 volt. This output voltage of the filter unit will be the input voltage of the voltage regulator unit. So, for instance, in your design, you want to use what? LOM7815. What they recommended the input, minimum input voltage? Eh? Ah. Class, what they recommended the minimum input voltage of LOM? LOM7815. What the minimum input voltage? 17.25 volt. But your input voltage is 15.57 volt. Is 15.57 volt greater than 17.5 volt or not? Eh? Is less. So from there, don't expect that voltage regulator to regulate and give you 15 volt. Because the voltage regulator is not an amplifier. That if you give the minimum voltage, it will amplify. No, it's not an amplifier. Are we together? So imagine that I gave you a problem, and then I ask you to use or to design linear power supply that provides 15 volt. What are you going to do? Because there you have seen there is a problem. So you have to refer what I taught you in previous workshop. So if you're just writing from there, you see the situation is difficult. And you will tell me that linear power supply cannot be designed. Because you just claimed always the output voltage of filter unit is 15.57. Are we together? Okay, fine. So go and find the minimum input and maximum voltage for the other. Just to try you to find for the 6. So how many remain? 18 minus 6 is equal to what? Ask your neighbor. 18 minus 6 is equal to what? 18 minus 6. 12. So you have to go and find for the other. If you won't find, okay, fine. Then we say that according to the data sheet of Johan, Hey. So according to the data sheets of LM78XXC and LM79XXC, the voltage regulator need two ceramic capacitors. Say two two ceramic capacitors. Mvuje Suleiman was happy. Mvuje Suleiman said that, today teacher. So these two ceramic capacitors. And those two ceramic capacitors, they have a fixed value, whether you're using LM7812 or LM7824. So the first one, the first task of the first ceramic capacitor is to remove the inductance of the unregulated signal. And the second one is actually to increase the stability of the voltage regulator. So the first thing, ceramic capacitor has, so the first ceramic capacitor has capacitance of 0.33 microfarad. And the second one the second ceramic capacitor has a capacitance of 0.1 microfarad. So the schematic symbol of voltage regulator, whether it is LM70, whether it's LM78 XS series or LM79 XS series, it just has 3 terminals. One terminal is inputted, the other terminal is ground, and the third terminal is what? Output. So whether it is providing 12 volt, or providing 24 volt, or providing 15 volt, or providing negative 18 volts, this is the schematic symbol of what? Of voltage regulator. So figure 4B, the schematic symbol of okay, so this is the figure 4B. So this is the schematic symbol of voltage regulator IC. So then, how do we connect these two ceramic capacitors? One of 0.1 microfarad and the other one for 0.3 microfarad. That's the next case, and then we go to the overall schematic circuit diagram of the linear power supply. So this is the input, and this is ground, and this is what is output. Submarine, please. Submarine. LOM 78XX or LOM 79XX. This is ground. So here we connect one capacitor in parallel, which is ceramic capacitor, and this is the symbol for the ceramic capacitor. And this one we have to connect it to ground, as usual. And then here we are going to connect the output terminal with another ceramic capacitor of what? So this one, the capacitance of this one is 0.33 microfarad, and the capacitance for this one is 0.1 microfarad. So the next part, or the next question, is what the functions of these capacitors. So this is figure 5C. So you say that the schematic circuit diagram of voltage regulator unit. So the next question, I think that if I could be you, stop writing. Stop writing. How are you? Are you real fine? Sure. Listen. If I could be you and I've been taught and I've been given the schematic circuit diagrams of voltage regulator unit, then I see two capacitance. So I see the first ceramic capacitor of capacitance 0.3 microfarad, and the second one is a ceramic capacitor of 0.1 microfarad. So I could have two questions. The first question, what the functions of each capacitor in that is schematic circuit diagram. The second question, how do we get those values? Why do we prefer 0.3 microfarad and not 0.4 microfarad? And why do we prefer 0.1 microfarad and not 0.0011 microfarad? Why? So if I could be you, I could ask myself those two questions. But because I'm not you, I just want to give you a few seconds to ask your neighbor. Could have asked those questions, or you could be asking about what time are we going to finish the class. Ask your neighbor, did you have the idea to ask about those two common questions? Ask your neighbor. Bundala. He's busy. Your neighbor is busy. I said stop writing. Ask your neighbor what the function of each of that capacitor and where did you get the values. So it means that, for example, this is Jessica and this is Joshua. So Joshua asked Jessica what the function of the each capacitor. And Jessica asked Joshua, how did we get those values? I think there the question will be balanced, yeah? Okay. Take your time. Ask your neighbor. Abdullah, ask your neighbor. Should I go far? Should I go far? Okay. I said, ask your neighbor. I will kick you ahead. Ask your neighbor. Whenever you come from my class, try to your level best to ask just to choose a good neighbor who will give you a cooperation. Because our neighbors, they are neither happy nor sad. They just want to talk, but sometimes they don't want to talk. Ask your neighbor. What's the name of your neighbor? Huh? Florence. So did you ask him? What did he say? You are still discussing. Continue your discussion. Ask your neighbor. What did you find from your neighbor? Amazing answers and amazing thought. So the answer, what the first question that they ask you? Firstly, what the function of the each capacitor? Why do you them? Right? So the answer of that function, we say that 0.33 microfarad is used to remove inductance. Inductance is used to remove inductance of what? Inductance within the unregulated input voltage. That's the function of the first capacitor with capacitance of 0.33 microfarad. So mark the answer of your neighbor. Mark it. Was it correct? Or it's not correct, or it's unknown. Then .1 microfarad is used to increase the stability of output regulated voltage. In some sources, if you read different sources, sometimes they don't mention the inductance. Say inductance. Say inductance. Why do we think about inductance? Because we have learned the principle of Ampere. Ampere's law, right? Or Faraday's laws, or Maxwell's equations. They have taught us whenever we have electricity, or whenever we have electricity, there is a magnetic field, or there's a magnetism. And whenever we have a magnet, we have also electricity. Right? So in most cases, the magnetic field, we measure them in terms of inductance. And why did we talk about inductance? Because remember that the input and the regulated voltage is come from the step-down transformer, where it comes from the secondary coil of step-down voltage. Are we together? So some sources, they don't mention that this capacitor removed the inductance, but they mention that that capacitor removed the noise. So whether they use the word noise or inductance, it's okay. And when you say noise, we don't mean that, for instance, I'm teaching and then you are laughing, or you are making some noise, or noise of the car. We mean about noise within the signal, or within the electric signal. We don't mean about the external noise that maybe the horns, the whatever, the ambulance passing by. No. Are we together? Are we together? So the answer of the second question, should I give you? I think that I have to leave it. Go and find. Yes. Go and find. How do you calculate this and this one? How do you get these values? So that's your homework. Will you go and find? Or you have found and then the information is not found? Huh? Okay. So if that's the case, so let me just help you to answer the question. The value of these two capacitors, we who are designing different systems, we don't calculate them. These are the values that manufacturer recommends to be connected externally. Kevin, I'm answering the questions which your neighbor has asked you. The answer is this one. The capacitance of 0.33 microfarad and capacitance of 0.1 microfarad is not a part of our design. It's not a part of our, that we have to use the mathematical questions to derive. It's according to the manufacturer. It's the manufacturer who gave you the data sheet and then gave you that schematic circuit diagram that in order to use the voltage regulator that we manufacture, you have to connect it to capacitors as external capacitors. Remember that the voltage regulator consists of transistors, bipolar junction transistor, and consists of resistors and roti and capacitors. But those should be connected externally. Okay? Okay? Good. So if that's the case, I think that I've given you some information about the voltage regulator. It's not all about the voltage. It doesn't mean that this is all about the voltage regulator, but at least you have a foundation. Ask the questions about what you have learned. Write that answer. Where should I write? Where? No, I can't write. You have to write yourself. Whether in your brain or whether you have to write in your brain, then write in your exercise book. So if that's the case now, we have to go to this part. The overall schematic circuit diagram, the overall schematic circuit diagram of linear power supply. So I ask you to write this title because I want to clean the whole blackboards because I need much space. So just write that subtitle. I'll be drawing that for the positive voltage. I'll be drawing for the negative. I'll be drawing for the more than one. If you want to design a single linear power supply. Oh, I think that before I talk about that once, I forgot. There's one important parameter. So you say that the standard output current of most voltage regulators is 1 ampere and the low level 1.5 ampere. This is very important parameter, especially if you are designing a huge system. So the standard output currents of most voltage regulators is 1 ampere and 1.5 ampere. Where will you know those informations? Whenever you buy any voltage regulator, you have also to refer the manufacturer or the data sheet of that voltage regulator. Where I think that next time I will teach you about the data sheets and how you can read and extract the information, because the data sheet can give you more than 7 informations about any electronics components or any electronics device. So from here, ladies and gentlemen, now let us draw some overall voltage or overall schematic circuit diagrams of positive, fixed. So let me add some information because now you understand. Fixed, positive, linear power supply. So write this title because I want to clean the whole blackboard, and I would like to draw this overall schematic circuit diagram with you, because we've been drawing step to step. The block of load is depend. For instance, that we are designing a small signal amplifier, so that will be our load. And then I just want to talk. I think that when I draw the schematic circuit diagrams, I will teach you. Once we have that output voltage, how can you connect to different parts of your circuit? Is it ready? Are you ready? So if you're not ready while we are finishing there, are you ready, or should I clean the whole blackboard? Should I continue to clean? No. You are a champion. You're a champion of what? Ready? Ready? Yes. Zuena, ready? Yes. Okay, so now stop writing, stop drawing. Pay your attention on the blackboard, please. But before you pay your attention, yes, I think that, okay, fine. Before you pay your attention, so let us go. So we don't have, we can show, we have to use, so we say that here, we are going to have, first of all, AC voltage source. AC voltage source. Urasa is what? Urasa is, okay, so this is, we call it alternator or voltage, AC voltage source. AC voltage source. So then we have 2 terminals of AC voltage source, which we will be assuming practically that this is all about 30. So I say this, stop drawing, stop writing. So then when we have this one, we are going to connect to the primary coil of the step-down transformer. Please check your neighbor. What is he or she is doing? So then, some of the, you might draw 2 bars of iron, or sometimes you might find even 3 lines. Should not confuse you. Whether 2 lines or 3 lines is still, because you have different types of these transformers. So either you find 2 lines, which represent the iron core, is fine. Or 3 lines, still the same. So this is all about the schematic circuit diagram of alternator. So this is AC. You might say that here we have 240 volts. So root mean square, like that. Then, listen. The next block, we say that's the bridge rectifier, right? Huh? That bridge rectifier, you have claimed the way of drawing it. But let me teach you another style that you can draw it. So, so you can draw those bridge rectifier in this style. So we are going to have 2 or 4 individual diodes. They are not connected in series, they are just connected in bridge form, just like this. Then we'll have other 2 diodes. Remember that I told you that at this time, you are right if you say that these diodes are connected in series. But when we change the configuration, you'll find that these diodes are not connected in series. Okay? Okay? Then we say that one terminal of step-down transformer will connect it here. So you may just name diode 1, diode 2, diode 3. I told you there's no need for you to claim about numbering. Then the other terminal of step-down transformer, we might draw like this to show that there's not any physical connection. We have to connect it here. Mexina, Mexina, Mexina. Okay? It's amazing. Right? So this is the bridge rectifier, like the one that you know we have taught you in advanced electronics, in advanced electronic science, we've taught you whatever, somewhere else, it's still the same configuration. We didn't change anything else. So go and think. If you do remember what I taught you in workshop 4, this is input 1. And this is input 2. If that's the case, this is output 1, and this is output 2. Simply we say that we'll be using this at the positive, and this one, Martha, 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 and this one. And then this one, we may use negative. So remember that we don't connect the transformer to the ground. Jacqueline, 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 Jacqueline. Student, please, whether online, whether offline, whether physical, pay attention. Pay attention, please. The information I'm teaching you, very important on your journey. Whether you like electronics or you don't like electronics engineering. As long as you are studying electronics engineering, there's no option for you to learn this information. So this is positive terminal. Then, the output of voltage regulator, we draw it from here to here. Okay? Eva, look on the blackboard, please. Then, if this is the output, the positive output, we are going to have a capacitor. And then we are going to have electrolytic capacitor. And this should be connected here. So this is our filter unit. This is a step-down transformer. This is rectifier unit. This is the filter unit. Okay? Okay? Please ask your neighbor. Look on the blackboard, please. Ask your neighbor, left and right. Look on the blackboard, please. Watatu. So then, the next block is what? voltage what? Regulator. This is the ground terminal. We have to connect it to the ground. Here we are going to connect all of these terminals to the common ground. This we call it in electronics common ground. Without common ground, your system will not work. Bonnie in this is ground. But we say that the voltage regulator needs ceramic capacitor, and this is the schematic symbol, of 0.33 microfarad. Ever look on the blackboard. Then here we are going to have another ceramic capacitor. Of 0.1 microfarad. So then, this is what we have been discussing in workshop 3, or in workshop 1, workshop 2, workshop 3, workshop 4, workshop 5. Okay, so we say that in order for us to have a visible signal that our linear power supply is working, it means simply we say that these are the two terminals where we are going. So here we have either, for this case, LM78XX. Case, you say that here we are going to have capacitance of 500 microfarad. And then for this case, we have N, we used to have 1N404, 4004. 1N or 1D, don't remember exactly. So this is the point where we are going to draw it. This is the point where we are going to draw the output voltage. So, in order to have assurance that our linear power supply is working, before we use it to power different parts, we always have power indicator, whereby we connected the light emitting diode that will be indicating that the power or the output, or we have now the output voltage at the output terminal. So for that case, we say that here we need to connect with a current limiting resistor to limit the current that will be flowing through a light emitting diode. The functions of light emitting diode is actually to give you a visible indicator of what? Of power, of working, whether your linear power supply works or it doesn't work. So here, this is light emitting diode. Light emitting diode, we just use 2 arrows, and this is the resistor. For this case, you may choose either 100 ohm or 240 or 300 up to 330 ohm. So let us just use, this is just to give us indication. It's not a path. It does not mean that if you don't have a limit, the current limiting resistor and the light emitting diode, your linear power supply will not work. It's not true. Okay? Okay? So again, remember that. This is one of our testing points. If you do remember, we call them testing point. Again, this is another of our testing point for the rectifier unit. This is another of our testing point for the filter unit. And then this is another of our testing point for the voltage regulator unit. Are we together? So listen, having a linear power supply, that's not enough. We have designed this linear power supply to provide the power in different subsystems of your electronic system or of the system that you are designing. So from there, we say this is enough. We'll have a wire, and then also we have another jumper here, where we have to connect this positive power into another component, we call it either connector or T-block. So this T-block will provide or will supply power. So these are the T-blocks. So you can find that this can provide power, provide power, provide power, provide power, provide power, provide power. But also remember that we have different parts of our electronic system that needs to be connected to the common ground, and the special common grounds of 40 of power. So here we are going to have a ground terminal bank, a ground terminal bank that will supply ground to different parts of your electronic system. So this we call it positive, or this we call it connector, and this one also we call it connector. So if that's the case, this is figure 5. Look your neighbor, what is he or she doing? The overall schematic circuit diagram of fixed positive linear power supply. So what the meaning of this connector and this connector? You do remember that we said in any electronic system we have 5 or 4 common blocks. Stop writing, stop drawing. Listen, look on the blackboard. Any electronics engineering system can be described into 5 or 4 blocks. This one we call the power supply unit. This one we call the control unit. This one we call the input unit. This one we call the output unit. And then this one we say this is data signal. And here we are going to have what data signal. But this is the power bank. So this one has to power control unit, has to power output, has to power input. So what does it mean? So from this point, for instance, we have a linear power supply. So having a single input or a single output for the linear power supply does not help us. Why? Because we can have the input units that need the power from this one. We can have the control units that need the power from this one. We can have the output unit need the power from this one. That's why when you design your linear power supply, you should provide also the power supplied by your linear or by your power supply into the banks. So for instance, this one will connect your will power input unit, right? And this one terminal will draw power from here to the control unit. Again, maybe you have a transmitter. So here we can connect our transmitter unit. Maybe you have another unit, which is actual that maybe we call it another part of the system. Maybe you have maybe a receiver unit, but maybe it's nearby within the same box. Maybe here you have another sensor that need a particular amount of what? Of power. Or we can say that we have a keypad. So it means that when you have a power bank, you can supply now your power to different parts of the circuit. Are we together? Are we together? Yeah. Should I repeat? Should I repeat? Eh? No. So are we together? Yes. Good. So similarly, because if we take this input supply or the power to the input unit, we also need to take its corresponding ground terminal. Again, if you use this terminal to power or provide the positive power to the control unit, then here we are going to have control units connected to the common ground. If again here we have a positive power fed to the transmitter, also you need the common grounds to be fed to the transmitter. So that's the process. But before you supply power, you have to be assured about the voltage supply. You have to measure it and you have to be sure whether it's 5 volt or 7 volt or 6 volt or 9 volt or 8 volt or 12 volt or 15 volt or 18 volt or 28 volt, 24 volt. Class, are we together? Eh? Okay, draw it now. I didn't tell you take a photo of it. I said draw it now. Okay, so this is a simple schematic or overall schematic circuit diagram of the fixed positive linear power supply. If we change the title from fixed positive power supply and make it a fixed negative power supply, so we just have to do simple changes. That here, instead of having M78XX, the only difference will be just having M79XX. Daniel, how many window cars have passed by you? So it is simple. So if you've been asked to design the fixed negative linear power supply, you have just to change the voltage regulator. That's all. Are we together? Are we together? But another thing that really may be my thinking, we expecting to get let's say negative 5 volts on this side. Where does it come from while we fed the positive voltage? You don't bother about that situation. But just the weight is coming around. That is number 2. So this is, so from the title, you can write that the schematic circuit diagram of fixed negative linear power supply. You redraw, but just you come and change. Don't say that, or don't think that I will remember to change 8 and write 9. Okay? Then the third case, in most cases of designing electronic system, because most of voltage regulator are limited in output current, which is either 1 ampere or 1.5 ampere. Sometimes you might design electronic system that needs power supply of 2 ampere. The total operating power for your system is 2 ampere. So for that scenario, you may not use the single linear positive power supply to power that system because it will give you only 1 ampere. So the other parts of your design, Kevin, will have insufficient power supply. Did you hear what I said? Did you hear what I said? Christina, did you hear what I said? Did you understand what I said? No. Christina heard, but she did not understand. So let me approach her. So, the case is this one. We say that in some designing of electronics or telecommunication system, you might do your designing and you need to use a linear power supply to power different subsystems of your system. But when you have done your design and then you've implemented your system, when you calculate the total amounts of operating power or the total amounts of power that required or that your system needs to operate, and you might be finding it is 1.8 ampere or 2 ampere or 2.5 ampere. So for that case, you may not, it means that if you may not use a single linear or a single fixed positive linear power supply to power your system because it's going to provide the currents of 1 ampere if you're using a voltage regulator that provide 1 ampere, or a current of 1.5 ampere, which is less than 1.8 ampere required by your system, or 2 ampere. Are we together? So for that case, whenever you encounter that challenge, and this challenge actually will encounter, if you've been loving this or designing electronic system, you will encounter, and especially if you integrate your system with communication unit. In case you need to design maybe a transmitter and receiver. So transmitter will consume large amount of power to propagate the information to the media. So for that case, if you use a single linear power supply of, let's say, 5 volts, positive 5 volts or 12 volts, will not be able to power all the system. For that case, you have to think about designing the dual power, or we call it just it might be just a single, might be just a fixed positive power supply, but you are going to have 2 different outputs. So you may design a linear, or you may design a fixed positive linear power supply that will provide different outputs of the same voltage or different voltage. So for that case, you'll just do nothing rather than what? Rather than just changing the configuration. So what are we going to do? Listen and look here. So I'm going to modify this systematic circuit diagram, and as the title, you have to write that overall, the title of your drawing, overall schematic circuit diagram of fixed positive linear supply of, let's say, 5 volt and a 12 volt, for instance. So for that case, what is going to happen? So for this case, we are going to have something like this. So here we are going to have, let's say, LM78 and then 05. Here we are going to have what? Common ground. And for this case, you say that we're going to have another, we have to connect these voltage regulators in parallel, not in series. You have to connect these voltage regulators in parallel. So look, so the input will be the same if the input will be the same and then we say that we are going to have a ground terminal. Remember that this is common ground. But also this one that we have to, should have another ceramic capacitor. So we'll draw the output from here. Then we are going to have maybe a resistor and light emitting diode to indicate the power flow. So remember that here there's no any physical connection. Then we say that this one we have to connect it with what? We have to connect it with a capacitor of 0.21 microfarad. And for this side also, we have to connect this input with a capacitor of 0.333 microfarad. So this possibly is LOM 7812. So for this case, you might have also another power bank that you'll be having here. Or you'll be just connecting your power to the another connector. This is the first connector, so you can draw your power at this point and this point. So here you are going to have, let's say, 5 volt, and the outputs of this point with these points will give you 12 volt. And this is 5 volt, which is separated with 12 volt. So 12 volt will be used to power some other subsystem, and 5 volts will be used to power some other subsystem. So this is in case you have designed the electronic system that needs different voltage for it to operate. But also you might, as I told you, that this one provides, let's say, 1 ampere, but you have a circuit which is total operating current or operating power is 2 ampere. You might also even have another voltage regulator here of LOM 7805, and this one will provide another 1 ampere. So if you have a system that needs 2 ampere, now you've solved the problem. Some of the subsystem will be powered by voltage regulator 1, and then some other subsystem will be powered by voltage regulator 2. So even if you need 3, so you can have voltage regulator 1, voltage regulator 2, voltage regulator 3. The principle, you have to connect them in parallel, and each voltage regulator need the capacitive, the ceramic capacitor of 0.33 microfarad and 0.1 microfarad. Even if that you want to design dual linear power supply, listen, even if you need to design, that's why that just I want you to understand, because if we say we draw the schematic circuit diagram, we might draw even 5 of them. Okay? If you've been asked to design a dual linear power supply, it means a linear power supply that provides positive 5 volts and negative 5 volts, or positive 12 volts and negative 12 volt. For instance, you want to design the one that we are using in lab. So it's simple. So it means that here you'll be having LOM 7812. This will give you positive 12 volt. Clean? Clean. Then this one you'll be using a voltage regulator of LM 7912. So this one will give you negative voltage. So you have negative voltage, positive voltage. So from this principle of connecting voltage regulators in parallel connection, it actually gives you understanding and the concepts of designing linear power supply that can power even any system that needs more than 3 ampere. So the principle is just you have to connect the voltage regulator in parallel. Okay? Are we together? Because you are the beginner, you might find that in all your works, a single linear power supply is sufficient to power what you are designing. But as well as you will be advancing, you will find that the single linear power supply, whether positive voltage or negative voltage, will not be suitable to power the system that you are designing. Class, are we together? Are we together? So the principle, you may even connect the 3 of them, but remember that when you connect them in parallel, you have to think about the step-down transformer. Because you might be looking for the output while the input is not okay. Are we together? Class, are we together? Eh? Is it clear or should I repeat? Remember, each voltage regulator, whether you are using 2 or 3 or 4, each voltage regulator needs the 2 ceramic capacitors connected in parallel. Are we together? Are we together? So we cannot connect 2 voltage regulators in series to design a linear power supply. Forget about that. We connect them in what? In what? Any question about what you have learned? Jacqueline, do you have any question? Happiness, do you have any question? No. Did you understand? Bundala? Bundala is still thinking. Sonia? Sonia? Huh? Anastasia? Do you have any question? Joan? Angelina? Namvua? Precious? Daniel, do you have any question? Omolo? Teacher Omolo? Glory? Matatu? Dominic? Do you have any question? Kevin, who has been somewhere? Do you have any question? Nura? No. Rollins? Dixon. Dixon, do you have any question? Dixon, do you have any question? No. Adam? Okay, so if that's the case, this is the end of workshop 5. Join me in workshop 60, where we'll be dealing with simulations of what you've been designing. So thank you very much. See you in the next workshop.